Hello all and welcome back. So in this video, let's continue our discussion and now try to find out the complexity of binary search. So let's get started. Now in binary search again, we were given a list or an array, right? We used to find the middle. Okay. And after that middle, you used to compare it. With the element you have. Again, now because we are talking about the worst case, we can of course be sure that we are not going to find the answer just in the first iteration. Rather, the full algorithm is going to work for all your recursive call, right? So we are going to understand the same using recursion, because binary search is a very good example of a recursive algorithm, right? Where we can use the recursion. The problem gets smaller and smaller, right? So what we actually do in binary search again is that we find out the middle. Like let's say we done some k unit operations in finding out the middle. Then once we have the middle, we call on either the first half or in the second half. So we first see what our number is. Okay, if let's say it is greater, then we will call on this half. If it is smaller, then we will call on this half. Right? That's the whole approach behind our binary search algorithm. So if I have to write, like we have already seen the recurrence relation for this, but if I have to directly write the time relation, I think it can be something like this. Tn is equals to k plus Tn by 2, right? So this is something which I just normally do. I do some k work. This k work can be something, let's say finding the middle, then finding out if the element is smaller or bigger, and then just calling the half problem, right? So this time I just make sure that I'm calling on the half. So let's say if I call on this right half, then I will compare this, then let's say on the left half. So every time my problem is just going to get reduced to half. So this is the overall relation which I am getting. My problem gets half, right? Now, if I actually have this relation, if I try to break it, or let's say normally if I just see with the lens of this half problem, with this half input problem, I can write down this relation. T of n by 2, okay, is equals to k plus, I'm gonna again do some k operations, n by 4, right? The same thing I could have achieved by substituting n by 2 in the first equation, but yes, the same thing is there, like because this time the input is half, this input is half, we are dividing again, after doing some k work, into half of that input. So half of n by 2 is n by 4, right? Again, if that's the case, then T n by 4 is going to become k plus T n by 8, right? I hope you get the idea, because we have done the similar kind of a thing in the last question. If we just keep on expanding on this for a very large input, finally when T is going to be 1, okay, for a array of index 1, we just actually check the base condition and we return, right? That is what we done. So we are just doing some k work. We are not making any calls. This time we are just doing some k works. If that is clear, let me write this as well, some constant work or operations, base case. Then again, the approach which I have to follow is that I will be adding all of them. This n by 2 gonna get cancelled, n by 4, again n by 8, and finally T1 will get cancelled. So what I'm getting finally is T of n is equals to k plus k plus k dot dot dot. How many times? Is it n? I don't guess it's n, right? It's not n. In factorial, we were sure that the problem is, because it was reducing by a single step, we were sure that okay, we are making n calls. But how many calls are we actually making for binary search, right? So that's the beauty and the complex part of this code, and let me explain you this beautifully. So let me just write it. How many times, right? Let's assume that it's x times. Okay, so I am just having this k x times. Now I have to find that x. Okay, let us understand what will be happening. We will be starting with a n. That n will get reduced to n by 2. It will get reduced to n by 4, n by 8, n by 16, and all the way I will be going till 1, right? So now if you can answer me that how many time I would have divided by half my n to get to 1, then I can tell you that okay, that number of time you have divided, that is the number of times your k will be, because that is what is happening, right? I started with the problem of n, then I divided it into n by 2, then n by 4, and just going on like this. I am finally able to understand this thing. Now, let us assume this is x, let us assume this is x, and what I can write is, so say x times to reach 1, okay? If that's the case, then n by 2x is equals to 1. I can write it like this, because at each and every of this step, I'm just multiplying by half, 1 by 2. So half x times, okay, it is just 2 to the power x, it will become, so n 2 to the power x is equals to 1. If that's the case, then I can write it as n is equals to 2 to the power x. There is a very beautiful mathematical function or operation known as log. So if I take log base 2 of n, I will get this as x log base 2 2. Log base 2 and 2 is 1. So it basically asks you that, hey, which power of 2 will give me 2? That's 1. So this you can change to 1. And finally, you get your x equals to log of base 2n, which is going to be your x. Okay. So I hope the whole approach is actually clear, way I have actually find out my x. Okay. You should be able to also now tell that how beautiful overall this binary search is. Just to give you a little bit better idea, first let me write down the complexity. This implies k plus k dot 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 log 2 n times, right? This further means I can write it as k into log 2n, okay? Which of course I can write less than k plus 1 into log 2n, right? If I can write this, then I can very easily say that time complexity of binary search is this is a very good complexity. Like if you can write a code for a problem which gets completed in log n, that's going to be the best code out there, honestly. Just to give you an idea, how good it is. Let us say that we have some 1 million elements. Okay, let's say we have some 1 million elements. And now to do the linear search on this, of course, we have to take 1 million comparison only, 1 million operations, right? Because we have seen in the largest array, the approach is going to be same. I hope by now your overall thought process will have also been built. That is something which I've actually been pushing you to make. Let us understand how many operations we will have to do for a million operations in binary search, right? So I'm going to use a calculator. So let's say log 2 of 10 to the power 6. 20 comparison just, right? So for 1 million elements, if we are able to just do 20 comparison, we will get an answer. That's how fast overall this log n is. Okay. And that was the reason, like anytime you will be running binary search and if you have a sorted array, doing it by linear search is going to be a waste of time. Binary search is always going to get you what you want. Okay. So yeah, that is the overall idea behind this particular approach, that using the line, I hope you're also able to understand how we have actually done this particular thing, how we have found this overall x, which is log 2n, and how fast binary search overall is. Okay. Great everyone. So I hope that is clear. Now, please make sure that you understand this approach pretty well. I don't want you to again remember the complexity. I am making sure that I am deriving everything in front of you so that you understand the process. That is very, very important. Okay. Cool then everyone. Let's meet in the next class. Thank you.